Hello everyone, welcome to the presentation of the paper Efficient Hardware Implementations for Elliptic Curve Cryptography over Curve448. My name is Mojtaba Bisheh Niasar and it's a joint work with Reza Azarderakhsh and Mehran Mozaffari Kermani. In this presentation, we will have a brief introduction on actually Curve448 and elliptic curve Diffie-Hellman key exchange protocol. Then we have an overview on proposed architecture and the implementation results and comparison. At the end, we have a conclusion. Let's start with the motivation of this work and some specific specification of the Curve448. As you know, the Curve448 is standardized recently by NIST, so the governmental organizations can be used of this curve for their crypto system. This curve also offers the higher security level after Curve 25519, which is actually targeted in our previous work. Furthermore, this curve is a suitable choices for actual combination with some post-quantum schemes such as Psych P434 to provide a hybrid key exchange protocol. Curve448 is designed by Montgomery and all actually safe curve policies have been considered during its design procedure. Although this curve can be known as a software-based design, our results show that this curve can be implemented efficiently on the hardware platform too. The curve 448 is a Montgomery curve and also can be known as an untwisted Edwards curve called ED448. There are only few hardware implementations of this curve. Azarderakhsh propose and actually an efficient hardware design based on the schoolbook multiplication for this curve. He also extended his work by adding some side channel countermeasures. Recently, Shaw actually proposed an LUT-based scheme, again based on the schoolbook multiplication. So as you see, there are only few hardware implementations and we need more investigations, especially actually for different, from different actually optimization perspectives, such as time limitation, area limitation, or a trade-off between them. Also, the curve 448 has some special actually features which can use, which actually results in very efficient Karat-Suba multiplication, which is not addressed in previous works. In our actually work, we try to address these actually these gaps to actually investigate different optimizations from different actually perspectives. Therefore, our contributions can be itemized as you see here. We investigate three different actually strategies: lightweight architectures, which targets area constraint applications; high performance architectures, which actually can be used for actually time constraint applications. Something between them, known as area time efficient architectures, which actually provide a trade-off between area and time. We also use different optimization techniques to increase our efficiency, including refined Karat-Suba multiplication, redundant number presentation, and interleave multiplication. We designed actually a process scheduling corresponding to each design to actually provide the required speed up compared to previous work. All of our actually implementation is a variable based point and is extended by side channel countermeasures. The elliptic curve Diffie-Hellman protocol includes actually the point multiplication. Therefore, both parties of the communications Alice and Bob should compute actually this point multiplication Q equal to K times P. P here is actually the base point and K is their own secret key. Therefore, all of these actual computations to compute this point multiplication should be performed over finite field arithmetic with P equal to 2 power of 448 minus 2 power of 224 minus 1. We use the Montgomery ladder for actually increase our efficiency, and therefore, based on the Montgomery ladder actual structure, 1 point addition and 1 point doubling should be performed in each iteration of the ladder. We use projective coordinates for this computation, and as you see, the required equations for computing X and Z coordinates for projective coordinates of point addition and point doubling are mentioned here. Here, as you see, we actually design our Montgomery ladder to decrease the required latency. As you see, we try to actually design a highly parallel structure to reach the total latency of A plus 10M, which A is equal to required latency for addition, for an addition or subtraction, and M is actually the required latency for multiplication or squaring. Therefore, we can actually design an optimized actually scheduling for performing point addition and point doubling in each step of the Montgomery ladder, as you see. We also consider different side channel protections in our implementation. All of our actually computation is constant time to avoid timing attack. We also actually provide secret independent implementations using the Montgomery ladder to avoid simple power analysis attack. We also actually embedded some countermeasures against differential power analysis attack to our in our actually implementation, including the point randomizations and scalar blinding introduced by Curve. The point randomization actually is used to randomize the P. As you see, the X and Z coordinates of the P is randomized by the random value of lambda. And in the scalar blinding, the second term of the multiplication, which is K here, is randomized by adding multiple of the group order to it. So it actually results in this method results in increasing the required latency because of increasing the length of the K, but the total, the actual final answer doesn't change. The top level of our architecture for different actually strategies is shown here. As you see, the design one actually targets the lightweight architecture using only one DSP. The design two is used for area time efficient architecture, and the design three actually is used for the high performance actually architecture using the 5-level consecutive crowdsourced multiplication. All of these actually arithmetic units are controlled by the controller, which is connected to the fixed program ROM, and actually they are also connected to a dual port RAM, which is controlled by the controller. Our lightweight architecture splits 448 bits input to 28 words of 16 bits due to actually the input size of the TSP block in the FPGA. So the data path in this design is 16 bits. We also actually perform all of the required computation sequentially to reduce the required hardware resources, actually utilizing only one DSP. The area time efficient architecture split the input to only 4 words using actually the redundant number presentation in 128 bits. Therefore, in this design, we actually use the fast Kurzweil multiplication, as you see, due to the special shape of the prime number in this curve. This equation has actually fewer actually elements compared to the original version of the Kurzweil. Some items actually can cancel each other, and therefore we use actually this equation in our implementation. We use actually the refined Kurzweil identity introduced by Bernstein, and as you see, the equation is mentioned here. Hence, the modular multiplication in this scheme is shown here. As you see, we use a 64 by 64 multiplication, which is fully pipelined. Therefore, the throughput is one output per cycle. Hence, it's 128 by 128 bit actual multiplication can be performed in 4 cycles. And actually the result can be accumulated by this circuit here. As you see, for performing A0 base B0 in this actually equation, or using the refined Kurzweil multiplication, we need only compute 3 actually multiplication, which needs only 12 cycles. The actually results of these 3 multiplications can be recombined to each other using the very actually optimized method. As you see here, we need only 5 operations in this actually recombination here. And also in the top level recombination, we again use an optimized actually method applying the interleave reduction on it. To actually provide an efficient implementation. In this method, in top level actually recombination, some components can cancel each other. In high performance architecture, we actually use a full 448-bit data path to reduce the required cycle of reading from the memory and storing to memory. In this actually scheme, we use the 5-level consecutive Kurzweil multiplication, as I said, and due to actually a number of available DSP block in our target FPGA, we have to implement the first level of this actually 5-level using the pipeline fashion. Therefore, the rest of the actually multiplication can be performed parallelly using 81 DSP blocks. Each of these actually multiplication can be performed only in 5 cycles. Therefore, the total required latency for our high performance actually architecture is 15 cycles. The performance results for all these 3 actually schemes can be shown in this actually table. As you see, the operation frequency in our design 1, which is our lightweight, is 250 megahertz. But in our actually high performance design 3, is dropped because of expanding the addition tree after actually that consecutive levels of multiplication. However, the total latency for multiplication is only 15 cycles. Therefore, we can actually compute a point multiplication in our lightweight design in 28.19 milliseconds. In our efficient architecture, it needs only 2.75 actually milliseconds, and in our high performance design, we need only 0.82 milliseconds for performing one-point multiplication. Now we compare our results to previous works. As you see, our design one needs a very few actually resources compared to all actually previous works. We also actually report some other actually FPGA implementations for different actually curves about 128-bit security. As you see, this curve needs very few resources at the cost of actually increasing the total latency. However, it can actually produce 35 operation per second. Our design 2 actually has almost the same actual latency for compared to previous works, while it needs actually fewer resources compared to previous works. For example, it needs only 16 actually DSP blocks, but the sausage needs almost 33 DSP blocks. Our high performance design also can increase the total operation per second compared to all previous works, while actually it needs more resources. We also actually reports here our high protected scheme employing the point re-randomization and scrub blinding. For better actually comparison, we try actually to visualize it. Here, the red point shows the unprotected scheme. The blue point actually shows the protected scheme, and the black point actually shows the high protected scheme, which use their point re-randomization. As you see here, our high performance design shows actually a considerable speed up compared to previous work with the same actually security level as you see, while it needs actually more hardware resources. There are actually design 2, which is our efficient design, has almost the same latency, while it reduces the required actually resources. And our lightweight design needs a few actually hardware resources at the cost of increasing the latency. Therefore, our design 1, which is our actual lightweight design, saves almost 96% of resources with the actually competitive performance compared to previous work. And our efficient actually design improves 48% of efficiency compared to previous work by occupying 52 percent fewer resources. And our high performance design improves almost 40% efficiency compared to previous work, and it can increase 12% actually throughput compared to the best previous work. To conclude, in this actually paper, we investigate 3 different hardware implementations targeting different optimization perspective. The first one is the area constraint application. The second one is the time constraint application. And the third one is the trade-off between the area and time. All of our architecture is implemented on a mid-range Xilinx FPGA. And actually, our implementation is a variable base point and extended by side channel countermeasure. As you see, we can provide different actually performance required for different actually optimization goal. Our high performance implementation can perform 1219 elliptic curve Diffie-Hellman key exchange per second, while our actually lightweight can perform 35 actually key exchange per second. Thanks for your attention. If you have any question, you can actually send me a mail or whatever you want. Thank you.